Welcome everybody in the lecture hall. Welcome everybody in Zoom. Welcome everybody from the future. Although maybe there may be more people from the future watching us today. Who knows, maybe from Germany as well. So I will start with vector databases. So last week, we've looked into the vector space model, which is a way to model the collections of documents as collections of vectors, where every document is a vector. And the coordinates of the vector, for example, can be taken as the TF-IDFs, right? Term frequency multiplied by inverted document frequency. Every coordinate corresponds to a term with some arbitrary order of terms. Then you have vectors. And then we saw that we have a measure of similarity between documents, between vectors, because now we can use the beautiful properties of linear algebra. We can compute the inner products, the cosine distance, and so on, renormalize. So this idea of having a collection of documents and querying that collection of documents as a collection of vector, in fact, made its way across the years, but I think that ChatGPT is probably responsible for that, into an actual database product where the vectors are actually central to the database. In fact, I'm considering adding vectors as a sixth shape of data, in addition to cubes, tables, trees, graphs, and unstructured data. I'm considering also adding vectors. It's been on my mind for a while now, so I might once take the leap. And so I told you at the beginning of the lecture, this is really a database lecture because a lot of the techniques that we actually cover are very similar to what you would have in relational databases or other kinds of databases. And so I added this new material this year. It wasn't there before, in order to show you how you can look at the vector space model from a database perspective and use SQL. So the idea, we took here PostgreSQL, which we use I teach an information systems lecture for non-computer scientists, and we already have a Docker setup with PostgreSQL, which we are reusing for that lecture with an extension called pgvector, which brings vectors into the relational database. What it concretely means is that you have a new type. You already know you have plenty of types in a relational database. It's the type of the attributes, right? You have integers, strings, dates, and so on. There is a new type called vectors. So a column in your relational database can be, in your relational table, can be a vector. So here we create a simple table with just two columns, an ID, which is just an increasing integer. And then we have the vector, we call that TF-IDF, because we are going to just put TF-IDFs in there, but we saw last time you can actually have other schemes of what you put in there. But let's say TF-IDF. And let's say we have 10,000 terms, so my vectors have 10,000 coordinates. So now I create this new table, and I can insert vectors in there. And the way I do that is just with classical SQL, insert into documents, that's the name of the relational table, and TF-IDF, that's my column. Not ID because this is automatic, right? It's a serial, it's going to increase automatically. And here, I can just insert my vectors. So the way it's done, and here, it's kind of breaking data independence, and that I don't like so much, but maybe in the future it's going to improve. You have to squeeze your vectors as a string containing an array. So that in the future, I hope, is going to improve at the language level for convenience. But this is basically how it is, right? You can put the vectors in that way as a string of a serialized array. And that's going to insert it's comma separated, right? Every array corresponds to a new vector. And here you have two rows, and you can have more and more rows, right? So you could potentially insert, I don't know, 1 billion of these vectors into the system. Of course, if you insert 1 billion, you're probably not going to do it with a SQL command like that. You're probably going to use better tools, but this is just to give you the idea, right? So at that point, we have a relational table in our database, and it's populated with vectors, right? We have maybe 1 billion vectors, each with 10,000 coordinates. And now what's beautiful is that I can actually use SQL, the good old SQL that you know. Who knows SQL? Everybody, right? We've all covered that in the probably the second year of your bachelor's. So the select from where that you all know, in the where clause, you can put whatever filter you want. So typically it's going to be comparisons, addition, multiplication, and so on. Maybe it belongs to a set or something. But now we have some syntactic extension with some other things you can do in an expression. And you see this seemingly weird sequence of characters with this smaller than dash greater than, right? And that is actually new. It's not normally part of the SQL language. And what it does is that it takes a vector, and it computes, in that case, the L2 distance. Remember what the L2 distance is? It's the square root of the sum of the products of the coordinates, right? So that's the Euclidean way of computing a distance. So basically, you have to see that just like you could have said where, if it were a number, where that column is greater than 2, or that column plus 3 times 4 is smaller than 5, you're working on individual atomic values. Here you're working on a vector, so you have the vector of the current record that you're testing, that's your current vector. And here you have a constant vector that you hard-coded into SQL. This L2 distance with this, so basically this computes the square root of the sum of the products, right? That gives you a number, right? That's the L2 distance, and then you can compare that number to 2, right? Who understands that query? Right? It's just selecting all of the documents such that the Euclidean distance of the documents is within a certain radius from a specific vector. So the vector, look at it as a point. It's a point in your vector space. You're looking at the disk that is centered on that document and that has a radius of 2, right? And you're selecting all of the documents that are within that radius. Who sees it now? Great, it's just a select from where. So now it's beautiful because we can just write this on a very high level, that we have a collection of vectors and we just filter the vectors that are within a specific distance of some other vector, which might be the query. For example, that what you write, the constant vector here, might be the query that the user just put in the system. And now you're looking for the documents that are close to that query vector, which is the results that we are looking for. Okay, now I told you there's other kinds of distances, right? So the people who designed the language had a lot of imagination, and so they made up some other sequences of characters. If my laptop would be so kind as to display the next slide, please. Pretty please. Oh, can you press again? Yes. So there's another sign with an equal sign in the middle instead. This one computes the cosine distance. The difference with L2, I think, is the renormalization, right? That you renormalize to 1. So it's the cosine of the angle. So in that case, by the way, I changed where to order by. So now what did I do? Sorry, I drank too much orange juice when I was writing that. It's either where and then you compare, or it's order by, but then you don't compare. I should remove the comparison on the right. That was silly of me. So basically what you want to do is order by distance, right? So you're going to output all of your documents and you are going to sort them by ascending distance with the query, and then you can add a limit 10, for example, if you want the first 10 results, and then it's going to work, right? I will remove that smaller than 0.1, which has nothing to do here. Now it's right. This one is right because it's a where. So the sharp sign gives you the inner product of the two vectors. Then you have the L1 distance, which is now, instead of taking the squares, you take the absolute values and you sum over them. So that's with a plus, so greater than, smaller than plus greater than. And you have the Jacquard distance. So the Jacquard distance is a variation of the Jacquard coefficient, right? I told you the Jacquard coefficient is not a distance because it varies in the other direction, right? It's actually large if the documents are similar and small if they are not. But you can tweak that with a fancy mathematical formula and turn it into a distance. So you get a Jacquard distance. And then you can also use that special with the percent in the middle. That's going to compute the Jacquard distance between the two. Right? So you see, all on the high level, just with the tip of your fingers, you can just compute all of these things and query for documents that are close to the query. You can nicely order them by distance. You can even combine where and order by with a limit clause and so on, and then find out the results you want to return, right? Oh, by the way, there's another one called the Hamming distance. You see there's a full menu of them. So here with a tilde, they're not all implemented. I think some of them are planned, but you get the idea, right? You can basically do all of that. But now it's beautiful because we have a high-level language, we have SQL, we have collections of vectors, it's nicely fully abstracted away. And you know what we love to do with database systems? We love to optimize. So it's like a game. You have the query language, it's supposed to return the correct results. And now you can tweak the implementation of the system to make it faster, but still returning the correct results. And this is actually where the fun starts for the database people. So we can optimize. And now in the coming hour and today, we are going to focus on how to optimize things in a way that we accelerate the computations of these distances between the documents. Now, if you remember, that's from last time, I suggested that you could, when you have a query, an incoming query, so Q would be the constant. Q, by the way, would be the constant vector that you have here. That would be Q. And you want to compute the distance. Now, you know that to compute, you need to compute a sum, right? You need to compute the sum of the products. And we saw that we can walk through the documents and walk through the terms and accumulate, right? It's just plus. So we have our buckets right there that are initialized to 0, and then we keep adding and adding the scores. We can either go term by term or document by document, right? We have two strategies to do that, but you know that this addition is commutative and associative. Who cares how you do it, as long as you accumulated all the correct terms inside the buckets, right? All right, so who is with me on that? We did that last time, right? Okay, so we need to accumulate. It's a variation of the standard inverted index. Instead of computing the intersection or union of posting lists, we accumulate these terms. So how can we optimize? Well, some of you who are very smart already figured out a few ways to optimize. So let's try to increase the efficiency. So what we can do first is that the query length is totally useless. It's a constant, right? So it doesn't affect the score. The score, we're only interested in the ranking, right? So we don't care about a constant factor, so we can get rid of the query. Then division by document length, that we can do at the end for every bucket. That also one of you figured out last time. So instead of doing it for every posting, we are going to just compute them with the buckets at the end. It's going to be less. It's still as many as documents, but at least it's no longer quadratic. It's no longer the product of documents and terms. So now we are left with this product of the TF-IDFs. Now, so yeah, we can also drop the accumulators for the documents that don't appear at all, right? If they are going to just be 0 the whole time with nothing ever added to them, we can get rid of them. So we keep these ones. Then for the query, this is the smart menu that I told you last time. You can take the TF-IDFs, but there's variations of that. And one of the variations is to not bother about the number of occurrences of terms in the query. Well, very often it's 0 or 1 because the queries are going to be simple. The only case where a query could have more than one occurrence of the same term is when you copy-paste error messages to debug, for example. So that might actually happen. But then you can simplify saying, okay, it's 0 or 1. Right? It's like the set semantics on the query side. So this is good because then if it's 0, then it's just that you're not adding anything. And if it's 1, then that just disappears, right? It's 1 times something, right? So this is good. This simplifies a lot. Now we have the IDF of the term, you see, is twice. So either you say, okay, we take the square of that and that's fine, but you know, it doesn't make such a difference to take the square, not the square. So you might as well on the query side, get rid of the IDF, right? So the IDF, that corresponds to the letter N. So it means that on the query size, we say 0 or 1 for the term frequency, and we drop the IDF, right? We don't multiply with the IDF. So now we are left with just summing over the TF-IDFs on the document side. That simplifies a lot, right? So this is basically a common way of doing that live. A very important remark is this is done at runtime. That you only do after the query is known. What you do at compile time before is build the index. That you can do at compile time. But at runtime, this is when you compute all of that. So you're going to have some algorithmic complexity in here that is roughly the product of the number of documents times the number of terms in a query, right? Who is with me? Okay, so we optimize a little bit. Now, let's try to push even more on the optimization side and get something even faster. There is a technique that is called Inexact Tom-K retrieval. And in fact, this technique is so important that it inspired many other techniques that we will see later, even in vector databases. So the way it works is to basically notice that the postings lists can be very, very large, right? Especially for the terms that are common in many documents. We have very large postings lists. So that's a lot to compute, right? The number of terms, mathematical terms, I mean, in that case, the number of terms in the sum to compute the distance is going to be very large. So what you can do, that's a lot of accumulators, right? It's we'd like to reduce that. Well, there's a trick. You can consider the whole collection of documents, the entire collection of vectors, and you pre-select a subset of that, roughly, approximately, right? You say, okay, rule of thumb, okay, I suspect that this is where the documents I'm interested in would be located. And I'm going to focus my computation on that part of the collection, and I'm dropping the rest. Now it's inexact because we might be missing out on some documents that would actually be interesting, but we didn't pre-select them. Bad luck, right? It's an approximation. We just assume that if we are good at pre-selecting documents and we have a pretty good approximation or heuristic of where to look, then we can just compute the top 10 and compute the distances within these pre-selected documents. So you see, it's not exactly the same. That's inexact, right? Because again, you're missing the documents outside. But this simplifies the computation because you're going to be much faster because you compute on less documents, and that accelerates the output. So the idea here, we'll look at evaluation soon, but I already told you about recall. It's a compromise between recall and speed, right? Either you want to have full recall, but then it's going to be slow. You have to do it on the whole collection. Or you accept to not have total recall, right? You don't have everything. You pre-select something, it's going to be approximate, but it's faster, right? So either you get the speed or you get the recall. Okay, so this is one technique. So how can we further drop stuff and eliminate things? Well, let me slightly change. Normally I put numbers in these purple rectangles. Let me, instead of numbers, tweak the height just to be visual, right? Instead of the numbers, I'm going to vary the height here. And that's the IDF. So the very rare terms have a high purple bar, and the common terms like end, that's the stop word, has a small bar, right? So what you do is that you eliminate end and school, which might be common, and ETH and Zurich you keep. And what actually happens, so now I just put the blue postings without thinking, but actually if you think about it, the ones that have a low inverted document frequency, so these are the ones that appear in a lot of documents, they have the longer posting list. So you see that now it's a double benefit, right? Not only do you query less terms because you drop the terms that have long posting list, but what you actually drop are the longer posting list. So if you look at the number of postings you're keeping, it's actually a very good deal, right? You keep the most relevant terms, and this happens to be the terms that have the smaller posting list, right? Who is with me? Okay. But in fact, we just reinvented stop words, right? And in fact, it's a common thing in the lecture, I hope you see, is that we are coming at the same ideas from different perspectives, but it's always the same ideas, right? So we just have yet another justification for dropping the stop words, those that happen a lot. Now, here's a second idea. You may have documents, so if this is your query, I just put the terms that are in my query. You might have some documents that contain all the terms. In fact, these would be the ones returned by a Boolean information system, right? It would be the intersection of the posting list, and you would keep them. But if you do this vector space model and accumulate evidence, then you don't do the intersection anymore. You just sum on everything, right? So you might also be summing on these kind of documents that contain a few terms. So the idea here is to do something sort of hybrid between Boolean retrieval and vector space models by saying that those documents that don't contain many of the terms, we will even exclude them from the sum completely, right? So we are going to drop them and only keep the documents that contain most of the terms of the query, right? It's a smaller sum. The problem is that you might be eliminating too many documents because there might be cases where there are synonyms, you know that it's not an exact word and so on. So the problem with that is that you're losing recall, right? You are going to have lower recall because you might be dropping too much information here. It's always a compromise to find. Okay. The next possible optimization is called champion lists. What is a champion list? Well, look at this posting list corresponding to a term. You have this purple box with the document frequency or the inverted document frequency, and then you have the postings. But now I'm going to do something. These postings, you remember that we store the term frequency in there. That's for use for the computation of our distance, right? So we not only have the postings, the document IDs, we also have the term frequencies. So what I'm going to do, now I also replaced my term frequencies with the height of the bar to be visual. I'm going to reorganize the order of the documents in my posting list, and I'm going to sort them by decreasing term frequency. So it means that instead of being sorted by increasing document ID, as we did until now, we're sorting them by decreasing term frequency. So it means that the first documents that I have in my linked list here will be the document that contain a lot of occurrences of the term, right? And what I could do is only compute the sum of the products for my distance for the top documents. I take the first R document where R is some number, that's some parameter, and I stop at R, right? I just take the documents where it appears the most. And what I can do is do it for every term, and I just compute a partial sum. I stop, I only take the documents that have the highest term frequency. For whom does that make sense? Right? So again, this is approximation. This is about approximating the results. It's going to change the correctness of the result. We might have differing scores, but it's an approximation that allows us to be faster in the way we return the results. R is typically chosen when you build the index, so you can do that in advance. You can even make R dependent on the term, right? For example, on the IDF, like if you have very rare terms, then you can increase R, so you can sum on more of the documents. And if you have stop words or words that are very frequent, then you can maybe sum on less, right? It's always a decision to make. It's the parameters of your system. Okay. Now, we compute the sum over the union of two of them. Now, there was a confusion last year. Somebody asked, why not the intersection? Normally, we compute the intersection of posting lists. But yes, but that's for Boolean retrieval that we do that. But here, it's the vector space model. We want to compute a sum. So if you compute a sum, it's the union. You need to include everything in your sum, right? But now, do you see a difficulty here with respect to the order in which I'm going to compute my sum, right? I told you, you can either go term at a time or document at a time, right? Term at a time means you take a term, you compute the sum over the posting list, right? Or the top R of the posting list, then the next term, then the next term. Document at a time is different. Document at a time is you traverse in parallel all of the terms by increasing document ID, right? So there's two ways of doing that. But do you see the consequence of taking the top R here on term at a time, document at a time? Who sees the problem here? Yes? Maybe we try to keep the habit of the microphone. I will increase the volume. Go ahead.
Hello, hello.
Yeah, we can hear you.
Yes, the document IDs won't be sorted anymore because we have sorted by term frequency.
Yeah.
So I guess we can't really do the going by document ID anymore.
So we cannot do document at a time anymore. You're absolutely correct. This is exactly the difficulty in here. We can no longer traverse and compute the distance document at a time because the order of the documents now is not going to be the same between the terms. Every different term has a different order. So it means that now you can compute term at a time, term after term, but you can no longer compute document at a time because the order is no longer the same. Who sees that? Okay. So you need the same order everywhere for document at a time. That's fine, right? We'll just do it term at a time, but it just reduces your options, right? You have less flexibility in the way you can sum. So what you can do, that's a way of circumventing the whole thing. If you really want to do it document at a time, you can keep the posting list in the common order, typically the order of the posting ID, but that could also be some quality score of the documents. And the champion list is separate, right? It's a separate structure. In addition, that you have an other posting list that might be sorted by document ID, but separate from the rest of the posting list, right? So that's one way to optimize. And then there is the super high level zooming out, powerful way of looking at it, which is if you sort in two ways. You sort by term frequency on the postings. So the high term frequencies on the left, the low term frequencies on the right, and you sort your terms by IDF. Normally, it's alphabetical, right? When you sort the terms, that's using your tree structure, and that's an alphabetical sorting. But instead of alphabetical, we are going to sort the terms by decreasing IDF, right? The rare terms first, and then the less rare terms. Now, if you look at this with a zooming out perspective, where are the documents we are really, really interested in here? If you look at all of here, where is the concentration of interesting documents? Top left, top right, bottom left, bottom right, where are they? Okay, let's vote. Who thinks top left? Who thinks top right? Who thinks bottom left? Who thinks bottom right? I think it's unanimous, right? Basically, everybody agrees that this is basically this part here. This here is what's interesting to us. This is where we have the concentration of information, because these are the rare terms and these are the documents that contain them the most. So technically, you go like this, right? You can basically focus on here, your calculations, then you can go a little bit down, a little bit to the right, like going in that direction, but you can stop whenever you want. You can maybe ignore that, ignore that, ignore that, but basically this is the zone where you want to compute, right? And here too, you can optimize by only computing a partial sum, but it's a partial sum on the parts that we are really interested in our collection, okay? That only works with term at a time, again. You cannot do it document at a time in that case. Okay, and a final idea, because there used to be more in previous years. I was throwing even more of that at you, but I tried to reduce it a bit this year to replace with vector databases so that you don't fall asleep, because that's actually a long list of optimizations. So the idea is that we have a problem with Inexact top K that we pre-select documents and we take the top 10. What if we don't find 10? What if in the pre-selection we only have 8 of them, or 7 or 5, right? And there could be some others outside of the pre-selection. Well, you can do that with tiered indices. It means that when you have this separate structure with the important documents, those that you pre-select, you can have another structure with the rest. So you can let the high list, the higher term frequencies, and the low list if you don't have enough results. And you just keep the low list as a joker. In case you don't have enough, then you go to the low list, right? So the idea is that you sort like this. You have your 3 parts, and now you have a first tier, a second tier, and a tier 3. And the idea is that you start with tier 1, and maybe now you have 10 documents, so you stop here. If you do not have 10, you only have 7, for example, then you go to the second tier, and you see if you find a few more. And if you still do not have enough, you go to the next tier, and so on. For whom is that here? Okay, so that's called tiered indices, to do it in this way. It's a bit adaptive. Okay, so now I'm going to move on to even more abstraction over that. It's even going to connect to machine learning. So if you take machine learning lecture, that might also mean something to you. And we'll connect it back to the vector database. Because we're optimizing things in there, but we still have to do a lot of sums at runtime. So that's still very costly from an algorithmic complexity perspective. So there is a technique called clustering. Who's already familiar with clustering in machine learning? Many of you, right? So I will not even explain to you how you do it in the detail, just on a very high level. The idea is that you have this vector space with all your documents. These are points in that vector space. and you are going to have clusters. There's many ways you can do clusters. You can do them with zones. You can do them with angles, like this. Pretty please. Maybe it thinks that I'm going too fast. That's went too fast. Or is it going on strike? I can just use my keyboard. All right. So the idea is that you randomly pick what you call leaders. It's a random collection of sub-collection of documents. You call them leaders. And then you look at the angles, for example, from the origin. That's one way of doing that. And then you take, for every document, you take the nearest leader, and that gives you a cluster, right? This is one way. Wow, okay. Okay, now it seems to be back to normal. So you take the nearest leader, and when you have a query, just look at the cluster that contains it, and then meaning you pick the leader that is closest to it, and that is less costly than the closest document because the set of leaders is much smaller than the set of all the documents. So that is less costly. Pick the leader, and then you compute the score only for the local cluster around your leader, right? That's one way of doing that. Who is with me? Okay. Now, let's get back to this vector database, right? Because on the very high level, I would like to compute my scores and my results with that, a SQL query. When you know that in a relational database, you can have indices, right? Hash indices, tree indices. Who remembers that? Right? Hash indices are very good in O of 1. You can have a lookup, and the tree indices are very good in logarithmic time. You can look up even a range. Well, it turns out that in the case, maybe that's the reason, actually. Maybe it's just a battery that is getting low. So we can just create an index, just like we can create a hash or a tree index. We can create an index that is very good at accelerating the distance computations. There's many of them, but there are mainly two right now in vector databases that are actually popular. The first one is called the hierarchical navigable small worlds, that is HNSW. And the other one is IVF flat, which means inverted file with flat compression, right? So these are two indices. I'm going to give you on a high level an intuition of how they work. And then you can specify with your index, it's like a menu. It's again a restaurant menu, right? Just like the smart scheme. So you can select your index and you can select the distance that you want to build the index on, right? You can say, okay, I want an index that is the small worlds index on L2, or I want an IVF flat index on Jacquard, and so on, right? And you just put it in the query. You put the index right here, and you put the sort of distance you want right there, and it's going to build an index. The look and feel of that is exactly like a hash index or a tree index. You're instructing the database system to build the index. You know that when you build an index, it can be synchronous or asynchronous, right? One way, if it's synchronous, it blocks the entire thing and then builds the index and then allows you to query again. Asynchronous means it does it in the background, and in the meantime, you're just going to be slower, but you can still continue to query. And then at some point, the index is built. What's going to happen? Well, what's going to happen is that when you write your query with select from where with the distance, it's going to be faster. This is the benefit of the index. But the query is still the same. You might be approximate, though. So that's an index that might affect a little bit correctness. It might be an approximation of the results, right? But this is, if you're aware of the limitations and of the assumptions that you have, then this does the trick. Again, it's recall versus speed, the compromise. But now, let's start with IVF flat, because in fact, that has to do with clustering. You basically build your clusters, as you saw on the other side, and then for each cluster, you have the inverted lists, the inverted posting lists that we have. And basically what happens is that the idea is that you have your query, you look for the cluster to which it belongs, and then you use the local inverted file. The inverted file is the name for the standard inverted index file. Okay? I'm not saying too much more. I want to stay on the high level, but this is the idea of the IVF flat index. And again, you have a pre-selection because you only compute on the cluster. It's basically the slide that you, okay, I think it's officially out of, oh, okay. I wanted to show you this one. Yeah. So the idea of the IVF flat is that you pick a cluster and you have the inverted index, but just for your local cluster, right? So that's the whatever cluster you are in. Okay. So that's IVF flat. Who is with me? Okay. Let's look at the other one. The other one is, sorry, the other one is the hierarchical navigable small worlds. So the idea is that I'm going to connect it to something we've already seen. Who remembers the skip pointers? We've covered that, right? It's a way to accelerate traversing a list when you have a small posting list and a big posting list, and you want to directly jump to further in the future if you know that you're not interested into a whole interval of postings. It turns out that we can generalize this to something called a skip list. And a skip list is basically a list of linked lists. Technically, it's many linked lists on the same that have the same data. You have at the bottom the skip list with the linked list with everything. So at the bottom you'd have the list of all document IDs, right? And then you build another linked list, but with a subset of the document IDs. And then another one with a subset, and you go up and up and up and up, and you have even less. Imagine that it's like the train network, right? You basically have the let's say you're walking on the bottom layer, then you can go with a bike on the second layer, you can take a train on the third layer, you could take a plane on the fourth layer, and so on. And it accelerates the travel, because if you would just do it, it would be just only walking if you do it on the bottom layer, but you can take the train and then bike and then walk, right? So this is the idea of skip lists. So you have this structure. And again, there is the dashed lines here show you that these are the same documents, right? So here, this is the same document, but you have this skip pointer that directly brings you here. Again, it's the same document. So you can start here, skip here, go here, go here, go here, and just navigate in any way you want, right? Who is with me? Okay. So this is skip pointers that was for posting list in order to accelerate the computation of union and intersection. Now, how can we apply this to our collection of vectors? In fact, we can. And the idea is that when you build indices, I already mentioned there's hash indices and there's tree indices. Turns out there's a third kind of index based on graphs. Hashes, trees, graphs. So basically, we do the same thing with a graph. It's exactly the same idea as the skip list, but instead of linked lists, we have graphs. So the idea is that all of these little circles here, these are my documents, these are my vectors. So if you look at the bottom layer, this is what has everything. You have the entire collection of all the vectors in your database, maybe 1 billion vectors. And you have these little edges that connect them to the nearby vectors, right? It's a whole triangulation, if you want to call it a triangulation. You triangulate the whole space, and then you connect every vector to the nearest neighbors. Now, of course, if you just have this layer, that will take forever, right? Imagine that you have a query that will be here, and you try to find the nearest the nearest documents. That can actually be a bit inefficient to find the results. So what you do is that, what you have is a higher layer with a subset of the graph, and yet another layer with a subset of the graph. And actually, you have this whole zoomed out plane that has only very few documents. And here it's super fast to travel around and find. And then you go down and down and down, and you start zooming in, and then you find the nearest zone, right? So this is how it works. That's called a hierarchical navigable small worlds. Okay, and of course you get that for free, because in SQL you just say create index. You just say create index using HLane.sw, and that does the trick. Okay, so these are the two indices that you can use. Okay. Now, let's zoom out at the whole architecture of the system. So putting all together what we've learned so far in the lecture, right? Oh, you have a question? Let me increase the volume too, to make sure. Go ahead.
Yes, about the last slide. All right.
I have to.
Because in a skip list, I get how we can navigate because we know that it's a sorted list, and if we want to get to like 15 from 1, we might as well skip to 10 or whatever. But how do we do the same kind of navigation in this graph? How do we know which direction to go to?
So, as far as I understand, because this is not something I know in detail, but my understanding on the high level is that it's a search problem. You have a query somewhere that is somewhere in there, and the query is closest to some document. You want to find the closest place. So you basically have something called an entry point that is in here. So imagine you start here. It's a random point that you start with. You enter the maze here, and then you have your query. What's going to happen is that you look at all the edges that are outgoing from that edge. You have some distance information. So you know for all of the edges that connect to that edge, you know how close they are. And you try to, how can I put that? You try to navigate to whichever, it's a greedy algorithm. You try to take the one that is the closest to the query. So you start here, you look at all of these that are around you, look at the distance to the query, and take the ones that is the closest. Then you go to the one that is the closest. If you are on that plane, that's very coarse, right? But at some point you go down, then you look at the closest one to the query, then you go down again, and then you are going to have some local minimum. It's a greedy algorithm, meaning it's not perfect, just goes to some local minimum. It might not be the global minimum, it might not be the closest, but it's going to be quite close, right? It's a greedy algorithm. Does it make sense? Right? That's on the high level. Of course, it's very complex to implement, but on the high level, this is how it looks like. Okay. All right. So now I might even have enough with my 5 minutes. Then in the break, I'll figure out there is another one here that I might be able to use. So the architecture of the whole system. So now what do we have? We have a collection of documents that we parse, we tokenize, we figure out the document IDs and so on, and we are going to build indices. So it's going to include all the indices we covered, right? The standard inverted index, we might have the byword version, k-gram indices, we might have permuterm indices, you know, all of those we covered, some positional indices as well with the places at which the terms are found in the documents, inexact top-K retrieval, zone indices that we also covered with relational-like library software. So these are all our indices, right? So we parse the documents, apply the linguistic post-processing that we spend a whole week on, and then we build our indices. Then you have plenty of query languages that you can support in your system. It's really a design decision, right? You pick the ones you want to support, but you see for every language, you have indices that can be useful, right? You can have, for phrase query, use byword indices. For field queries, like in library software, you use the zone indices. For you can use the vector space model if your query is just some set or bag of words in general, but basically use the vector space model. Wildcard queries, you can use the permuterm, k-gram. That's just a summary, but we've covered all that, right? These are all the languages you can have. If you look at a search engine like Bing or Google, it's kind of doing everything, right? It's kind of trying out as a phrase, trying out as a Boolean. It kind of smartly figures out how to interpret your query, but it's really a mix of all of that in the end. For example, these field queries, you know that you can use the site colon and then a domain. You can have modification dates. I mean, there are ways to type under Google, even though not everybody knows these tricks, but you can. So you parse. You might also cache your documents. Why? Because you want to display snippets in the results, right? You might want to display in context. So you might want to cache your documents. That's what is called downloading the entire internet, right? Then you have the indices. Then you have the query that comes in. So this is compile time, this is runtime. The query comes in, you parse it. You might apply some spell correction. We've already covered that. And then you look up in the index. And what you do then is that you accumulate evidence. Accumulating evidence is the idea of traversing term at a time, document at a time, summing over the postings and accumulating the additive terms, the mathematical terms of your sum. That's called evidence accumulation. Now, there are parameters as in that called weights, and that you can use with machine learning. You can figure out the weights that you put in there, right? So that's a separate system that is also done separately, but you figure out your parameters by using a training set. And finally, you display the results to the user, potentially with the snippets. All right? So you see, everything is in there. What we've done all of these weeks, everything is in there, just fits together and with different languages, different query systems, optimizations, and so on. Who is with me? Okay, I think you deserve the break. After the break at 15 past, we are going to cover evaluation, how to evaluate how good a system is, precision, recall, specificity, and so on. And I realized that my watch is actually now 1 minute off, so I need to be careful. So see you in 15 minutes after the break. Thank you.